Today is Wednesday. I haven't do exercise because I wake up late. I feel so tired. I will put this in the bottle. I will put this in the bottle. $20,000. Bam. That's a lot. Then I will write the amount of money that I have just put. Oh, the topic is here. The topic today is about the life cycle of the neutron star. Oh, the weather is start to rain. Oh my god. About once every century, a massive star somewhere in our galaxy runs out of fuel. This happens after millions of years of heat and pressure have fused the star's hydrogen into heavier elements like helium, carbon, and nitrogen, all the way to iron. No longer able to produce sufficient energy to manage its structure, it collapses under its own gravitational pressure and explodes in a supernova. The star shoots most of its innards into space, sealing the galaxy with heavy elements. But what this catalytic eruption leaves behind might be even more remarkable. A ball of matter so dense that atomic electrons collapse from their quantum orbits into depths of atomic nucleus. The death of that star is the birth of a neutron star, one of the densest known objects in the universe, and a laboratory for the strange physics of supercondensed matter. But what is a neutron star? Think of a compact ball inside which protons and electrons fuse into neutrons and form a frictionless liquid called a superfluid, surrounded by a crust. This material is incredibly dense, the equivalent of the mass of a fully loaded container ship squeezed into a human hand, or the mass of Mount Everest in a space of a sugar cube. Deeper in the crust, the neutron superfluid formed in different phases that physicists call nuclear pasta, and it squeezed from lasagna to spaghetti like sex. The massive precursors to neutron stars often spin. When they collapse, stars that are typically millions of kilometers wide compress down to neutron stars that are only about 25 kilometers across. But the original star's angular momentum is preserved. So, for the same reason that a figure skater spin accelerates when they bring in their arms, the neutron star spins much more rapidly than its parents. The fastest neutron star on record rotates over 700 times every second, which means that a point of its surface whirls through space at more than a fifth of the speed of light. Neutron stars also have the strongest magnetic field of any known objects. This magnetic concentration forms vortices that radiate beams from the magnetic poles. Since the poles are always aligned with the rotational axis of the star, the beams spin like lighthouse beacons, which appear to blink when viewed from Earth. We call those pulsars. The detection of one of these tantalizing processing signals by actual physics, Jocelyn Bell in 1967, was in fact the way we incredibly discovered neutron stars in the first place. An aging neutron star's furious rotation slows over a period of billions of years as it radiates away from its energy in the form of electromagnetic and gravity waves. But not all neutron stars disappear so quietly. For example, we have observed binary system where a neutron star co-orbits another star. A neutron star can fit on a lighter companion, charging on its more loosely bound atmosphere before eventually collapsing cataclysmically into a black hole. While many stars exist as binary systems, only a small percentage of those end up as neutron star binaries. When two neutron stars circle each other in a way doomed to end as a merger. When they finally collide, they send gravity waves through space-time like ripples from a stone thrown into a calm lake. Einstein's theory of general relativity predicted this phenomenon over 100 years ago, but it wasn't directly verified in 2017 when gravitational wave observatory LIGO and Virgo observed a neutron star collision. Other telescopes picked up a burst of gamma rays and a flash of light, and later X-ray and radio signals are from the same impact. That became the most studied event in the history of astronomy. It yields a treasure trove of data that have been down the speed of gravity, bolster important theories in astrophysics, and provide evidence for the origin of heavy elements like gold and platinum. Neutron stars haven't given up all their secrets yet. LIGO and Virgo are being upgraded to detect more collisions. That will help us learn what else the spectacular demise of these dense, pulsating, spinning magnets can tell us about the universe. And this law